Our first speaker is Harley Meade from Colorado State University, who will be speaking about characterizing ETFs through combinatorial methods. Take it
Thanks,
away,
Stephanie, and
Harley.
thank you to the organizers of the conference. So first off, what is a frame? A frame is some spanning set of vectors for whatever space it lives in, and it's going to act as a kind of normally redundant generalization of an orthonormal basis. And redundancy, a lot of people don't like, but it's actually good in this case because this will contribute to things like signal processing and quantum information. So like redundancy is good. We want that. More specifically, a frame, or at least a finite frame, which is what I work with, is some ordered collection of vectors with constants A and B satisfying this inequality. And just as a point of note, phi, we can think of it both as the set of vectors itself, but also the matrix whose columns are the vector. Kind of an abusive notation, but it's pretty standard. So if we have that these bounds are equal, our frame is tight. And if we have that all of the vectors are unit norm and there is some positive alpha such that for all distinct pairs, the inner product, the absolute value of it is equal to alpha, we call the frame equiangular. And the reason we want this absolute value is because we're not necessarily thinking of just the vector, but the line it spans, and then looking at the non-obtuse angle between them. So a unit norm frame that's both tight and equiangular, creatively named equiangular type frames, or ETFs, and that's what I work with. So I mentioned that the redundancy is good, and we have kind of ways of quantifying that, specifically how much it's spread out. And so one way to think of the frame being spread out is with geometric spread, and that's going to be related to the angles between vectors. So we have this term coherence, which is the maximum of the pairwise inner products over the norms. If you have a unit norm frame, which normally you do, this is just the maximum inner product. And since the inner product is bigger when the angle is smaller, we want the coherence to be kind of as small as possible because we want the vectors to be spread out. And so we have this Welch bound that bounds it below. And it's also related to the spark, which I'm about to define, but we're not going to get super into that. So algebraic spread is what I deal with more. And that's going to concern the linear dependencies of the vectors. And so the spark is going to be the minimum number of linearly dependent vectors. So if you think of a matroid of the columns, this is the same thing as the girth. And if the spark is d+1, where we're living in d-dimensional space, we call our frame full spark. So full spark frames are really nice. These are like the best for sending information because they are maximally robust to erasures. And here, if we have that the minimum number of linearly dependent vectors is d+1, then every subset of d vectors is going to be a basis for FD. So going back to the matroid notion, this means that it's the uniform matroid of rank D on n elements. And we can also say that if we have some d by n matrix phi, this is full spark exactly when every d by d square submatrix is invertible. Cool. So there's, like most mathematical objects, there's some sense of duality. And if we have some type frame with frame bound A, then we can expand this to be a square matrix that's n by n, to where the rows form an orthogonal basis for Fn. And we label the matrix formed just by the new rows psi, and psi is going to live in n minus d dimensional space. And we call psi the Naimark complement of phi, but basically you just have to think of it as sort of the dual. And the Naimark complement of a type frame is again going to be a type frame. And if phi is equal norm or equiangular, psi is as well. And in particular, the Naimark complement of an equiangular type frame is going to be an equiangular type frame. So if we have that phi is some type frame with Neimark complement psi, then the dual of the matroid formed by the columns of phi is going to be the matroid formed by the columns of psi. That's non-trivial, so I'm not going to go into it, but it's very useful because that gives us that if phi is a type frame with Neimark complement psi, phi and psi are full spark at exactly the same time. Because if you're looking at the dual of the matroid of phi, as I said a couple slides ago, that matroid is going to be the uniform matroid of rank D on n elements. Dual of that, uniform matroid of rank n minus D on n elements. And that's the matroid of psi. So since the matroid is uniform, it's full spark. Yay! That's going to be helpful here in a little bit. So one last big definition before I start moving towards what I've been doing. The discrete Fourier transform matrix is a n by n matrix that is powers of zeta, where zeta is a primitive nth root of unity. And if we had multiple roots of unity, I'd probably label this zeta n. But also note that this is the character table of Zn, and that's just going to be a little bit easier notationally to deal with here in a second. But essentially, it's the powers of zeta to where 0th row, all ones, first row, zeta, zeta squared, and so on, zeta squared, squared, and so on, all the way down to zeta to the n minus 1, and then powers of that. So this definition here has been the basis for what I've been doing for the past 8 months now. And this is from a paper by Alexeyev, Cahill, and Mixon. If we have some subset of Zn, not a subgroup, just a subset, different sets work pretty well here, but we say that it is uniformly distributed over the divisors of n if for every divisor of n, the cosets of the subgroup generated by the divisor partition your subset into smaller subsets that are basically the same size. So this floor and ceiling means they're going to differ by at most 1. And this isn't always going to happen. In fact, it doesn't happen that often. But when you do, if you have n is some prime power, and you select rows from the n by n DFT that are indexed by some subset m, the submatrix that you form is going to be full spark if and only if the subset that you're indexing by is uniformly distributed over the divisors of n, which is kind of cool. This was an attempt at generalizing Chabaterov's theorem, which says that if you have a prime, then any square submatrix of the p by p discrete Fourier transform matrix is invertible. And the reason that that's a generalization of this is because if you have some prime as your n, then here the only divisors are 1 and the prime itself, so it kind of trivially partitions it into the correct size subsets. So I've been working on trying to generalize this for non-cyclic DFTs. And by non-cyclic DFT, what I really mean is I take some cyclic DFT and Kronecker it with another one. So in this case, looking at prime powers, but now instead of just n, this is the cyclic DFT, I'm looking at the p by p DFT Kroneckered with itself k times. So here, if you have some prime power, n is p to the k, and k is not 1 because otherwise it's just the Chabaterov's theorem. And if you have d between n minus 1 and n minus n over p, or d is between 1 and n over p, then no d by n submatrix of this DFT is going to be full spark. And the reason that I'm excluding the 1 and the n minus 1 here, well, if you have 1 row, then being full spark is equivalent to not having a 0 entry, which we won't in a DFT. And then the n minus 1 is going to be the Neimark complement of it. So since the 1 row is full spark, n minus 1 is going to be full spark as well. And generalizing off that notion, since a frame is full spark exactly when its Nymark complement is full spark, you can just think of the lower half of this. So 1 is less than D, less than N over P. This is very non-trivial to show, but kind of annoying, and it was mostly just a lemma, so I decided to ignore it. But other than that first row of all ones, every row is going to have exactly N over P ones, which means that every row is going to match the first row in N over P places. So if you label the rows with the elements of ZP to the K lexicographically, then you can think of ZP to the K as a group acting on the rows in kind of the way you would expect. And so that means that if you take two rows that are shifted by the same element, since what's really happening with that group action is multiplication by a diagonal modulation matrix, if two rows are shifted by the same element, where they matched before is going to be exactly where they match in the shifted rows. So that means that if you have some submatrix with D rows and all of the columns, then the first two rows, you can say, okay, the first one is a shift of the first row, like the all ones row, and then the second row is a shift of some other row by the same element. And by what we just said, this means that they match in N over P columns. And I labeled the columns that they match J1 through J N over P. Since we're assuming that D is less than or equal to N over P, we can look at the submatrix of D that has all of the rows that we're left with, and then columns that are the first D of these J. So we have a square D by D matrix. Since we specifically chose the columns that they match, the first two rows of the submatrix are exactly the same. And so this little square submatrix is going to be rank deficient, and thus it's not invertible. So we have that D is not full spark. Notice here that in the case that P is 2, this encaptures all of the rows. So if you have a Sylvester-Hadamard matrix, which is the P equals 2 case here, then no D by N submatrix of this is going to be full spark other than the trivial cases of 1 row or N minus 1 rows, which is kind of neat. I've also been wanting to play with non-prime powers because even if we're getting past the cyclic case, prime powers is still a fairly small portion of possible choices. So here I want to look at the ZM by ZN DFT matrix. So here, when I say the ZM by ZN, I mean this is the character table of the group ZM cross ZN. And specifically, this is the case where N is a multiple of M. So if we have this matrix and Fm is the M by M DFT, Fn is the N by N, rows labeled lexicographically, the minimum number of ones in each row is going to be M. And further, if M is a prime power, again, prime power case, but what can you do? We know exactly where this bound is saturated, and that's going to be in rows JK, where if row J in Fm is generated by a primitive mth root of unity, then row K in Fn is not generated by a power of zeta n to the P, where P is a prime that divides N over M. And if row J is not generated by a primitive mth root of unity, then row K is generated by a primitive root of unity. A lot of casework went into proving that. Going off that, numerically, this seems true, but even more casework, and I haven't finished the proof yet. But this is when N is not a multiple of M. The minimum number of ones is going to be the GCD of M and N. And then this bound will be saturated in rows LK, to where L is not a multiple of a prime that divides M over D. K is not a multiple of a prime that divides N over D. And if L is a multiple of the GCD, then K is not a multiple of any prime factor of N. So kind of a lot going into that, but I think I'll be able to prove that soon. Future work, other than finishing that proof, generalizing the definition of uniformly distributed subsets for non-cyclic groups, because right now it is only cyclic groups, and specifically for those of prime power. I also want to not only find the minimum number of ones in each row of a non-cyclic DFT, but fully find the number of ones in it, because once you know the number of ones, then you can say, ah, yes, these rows will be good or these rows will be bad in finding full spark. And finally, I want to generalize these theorems to where you have the Kronecker product of more than 2 cyclic DFTs, to where eventually I could characterize all finite abelian groups. Thank you.
All right, let's thank our speaker either by unmuting and giving a round of applause, or using the applause react, or saying thank you in the chat. And what questions do we have for Harley? I see Galen is asking if you have any preprints out about this.
Not yet. I have just like a random list of things that I have proven that has mostly just gone between me and my advisor so far, but hopefully in the near future.
What other questions are there?
So back in your definition of frames, you have this sort of like upper and lower bound as part of the criteria. Is there some sort of like geometric or algebraic intuition that we should use for like what that means, what that restriction is?
Not off the top of my head. Basically, you're saying that the norms of the vectors in the space bound the inner products with the frame. I don't think of things geometrically, frankly. So not quite sure. Maybe I can ask Emily for you though.
Sounds good, thanks.
I see in the chat excluded minor. I don't think I've seen that in like the papers I've been reading more thoroughly, but it may have come up in one of the like background papers that I've read.
Another question. So is there anything more that you could say about which minors precisely have full rank and which don't? You were able to find that some don't, but is there anything more that could be said where we could actually pick out which ones are invertible and which ones aren't?
The proof that I used is which ones don't, kind of. Let's see if I can find this. We're basically looking to see where the second row in whatever set of rows we're looking at has ones, or where the unshifted one would have ones. And that's going to depend on which rows it generates, because if you look at the definition of DFT, if this isn't prime, then a lot of these are going to have like repeated ones over and over again, because like say we were doing the 4x4, the 0th row would be all ones, first row all of the entries, second row would be 1 zeta squared 1 zeta squared. And so it's really just going to depend a lot on what your M and N are. Yeah. I'm used to working with similar stuff over with Zmod 2, and so stuff like this has been popping up. So, gotcha. Yeah. Okay. Yeah. Thank you. I don't know what equivalence of norms is, so possibly. The question was, does your inequality in slide number 2 relate to equivalence of norms? Very possibly. Who knows?
Right. Are there any more questions for Harley? Okay, let's thank our speaker one more time then.